All right. Welcome to Friday, everybody. So, a guy went to a doctor, and he said, "Doctor, I'm addicted to Twitter." And the doctor says, "I don't follow you." Yeah, not bad, huh? It's always good when I see some nodding heads after a dad joke. I refuse to acknowledge the shaking heads today. Okay, so let's take a look at simple harmonic motion worksheet number 1. We'll just go through this step by step, and after that, we'll take a look at some of the other stuff. So number 1 says you have a pendulum of length 0.75 meters. Find the period of your pendulum. So, period of a pendulum is just 2 pi times the square root of the string length divided by g, 9.8 on Earth. So if you plug those numbers in, the length is 0.75, g is 9.8, and when you run that calculation, you're going to get a period of 1.74 seconds. So that one's pretty straightforward. Now number 2 says, what would happen to the period of your pendulum if you increased the pendulum length? Who can help me out with that? You make the string longer. What happens to the period? Yeah, the pendulum slows down, the period would increase. If you look at the equation here, if we increase the L, that is going to increase, the value of the calculation. Letter B, what happens if you increase the release height of the pendulum? Then what happens to the period? By our experiments yesterday, nothing, yeah. There is no release angle in the equation here, so that's not going to affect it. Because if you release it from higher, it's going to travel faster and cover more ground. So, even though it's moving faster, it's traveling through a larger area. It would take the same amount of time as though it was moving slower through a smaller area. Letter C, what happens if you increase the mass at the bottom of the pendulum? What happens then? Nothing. No change whatsoever. So that would also be nothing, because you notice in the equation here, mass is nowhere to be found. Number 3, now we have a nice little story. Congratulations. Did I say yesterday this is the very first worksheet I ever created? No. Okay, it is. Yes. Congratulations. It was for an assignment in one of my classes in college. So we had to make it really fancy and stuff. You've won a trip to the moon and have decided to bring along your pendulum. The moon's gravity is much weaker than the Earth's. What do you think will happen to the period of your pendulum as you measure it on the moon? So what's going to happen to the amount of time it takes for that pendulum to swing back and forth once? Will that time grow? Will it decrease? Or will it stay the same? Exactly. If we decrease this g value here, that's going to increase the calculation on the left, because this is in the denominator. So that makes this number bigger. And the question is why then? Because gravity is lower. Number 4. G on the moon is 1.6 meters per second squared. What do you measure the period of your pendulum to be there? And does this match up with your prediction? So now it's just a matter of using the same numbers that we did before. This was 0.75 meters, and this g value was 9.8, but now we're on the moon, so we're just going to plug in 1.6. And if you run those numbers, you're going to get a time of 4.3 seconds. Way longer than the 1.74 seconds from the previous page. So that's number 4. Everybody still on the same planet? Or moon, I should say.
That's pretty simple.
Good. Now we're going to a different place. Number 5. Your best friend has won a trip to Jupiter. and took your simple pendulum without asking. Jupiter's gravity is much stronger than the Earth's. What do you think will happen to the period of your pendulum as your friend measures it on Jupiter? So now what's going to happen to it? Greater than, less than, or equal to what it was on Earth? Thank you. Less than, exactly. When you increase that gravitational value for G, that means that your denominator is growing, and when your denominator grows, your final number is going to get smaller. So yes, it will be a much smaller value. That pendulum is going to swing back and forth very quickly on Jupiter. Number 6, the gravitational acceleration on Jupiter is 26.7 meters per second squared. What does your friend measure the period of your pendulum to be? So again, the length is the same value, 0.75 meters, and now G is 26.7 meters per second squared.
It's always during this hour.
I know, right?
Jeez.
So when you run the calculation this way, as you'd expect, we get a much smaller number than on Earth. 1.05 seconds is how long it takes for the pendulum to go back and forth once. So almost half the time of Earth. And finally, number 7. We have the conclusion of our story here. You're angry at your friend for stealing your pendulum, and so you shoot off into space looking for him. Before leaving, you create another pendulum. This one's only 0.5 meters long. Eventually, you crash land on a strange planet and measure the period of your new pendulum to be 1.33 seconds. Calculate the gravitational acceleration of the planet you landed on. So let's do that first, and then we'll finish up the rest of this question. So now, you've got a different pendulum. No longer is it 0.75 meters long. Now it's half a meter long. And you measure the time it takes to go back and forth once, and it's 1.33 seconds. So we got to figure out if you're on the right place. Are you on Jupiter, where you can then find your friend and exact your revenge? So if we want to do that, we kind of have to do the same thing we did yesterday when I was telling you about, the pit class, and I solved for the length of the string of the microphone. So instead of solving for L in this case, now we know what L is, and we know the period, so we have to solve for G. So let's go ahead and give that a shot. So if I want to solve for G, I got to square both sides to get rid of the square root sign. 2 becomes 4, pi becomes pi squared, and then we just have regular L over G. So now if I want to solve for G, I would just think of multiplying both sides by G, and then I'd want to divide both sides by t squared. So the G comes over here, and then if I divide both sides by t squared, I'm going to have 4 pi squared L in the numerator. And then I'm going to have t squared in the denominator. And let's see what we get. All right, so I got about 11.2 for my G value. Is this Jupiter? No, we landed on the wrong place. So now we got to figure out if we overshot or if we undershot our desired location. So if you actually take this G value and you, what's that? Neptune's right on the money, yeah. You just have to look online and you can find the G value of the different planets in the solar system. And lo and behold, 11.2 matches up with what Neptune is. So you have overshot Jupiter by 3 planets. What's that? Yeah, and they actually don't have solid surfaces either, so you couldn't walk around, but we're just having a good time here. Any last questions on this worksheet?
No.
Okay, sounds good. I'm going to come around and get that from you. 14.